In the previous video we were talking quickly about how you can integrate numerically the equations of motion so that you can predict future vehicle trajectories. So you can say, well, if we know the forces, we can compute the accelerations, and if we know the accelerations, then using calculus we can get velocity, and once we know velocity, then we can get position. And that's what we really care about, is where it ends up and how fast it's going to get there. So one way to do that is to use regular calculus. So assume that you have some function, f of x prime. You can integrate it with respect to time, and from some time 0 to some time final, and you end up getting the function that you're originally looking for. So that's one way you can do it. Unfortunately, for the equations of motion of spacecraft, if you want to do it really well, you have to do it, or especially if you want to do it very accurately, you have to do it numerically. And what do I mean by numerically? So this actually breaks down for some types of equations. It doesn't work for some types of equations. For example, it breaks down for gravity, because gravity is very nonlinear. And it also breaks down for some other things. So as a result, we have to use numerical integration schemes. In the previous video, I mentioned that we could use what's called the Euler integration scheme, which is very simple. It essentially says that, x at some time in the future, x plus at some time plus some small time step in the future is equal to my current time, or my state right now. So this is my state right now, x of t right now, plus my rate right now times my rate right now times some delta t. And this is very, very simple. It's called Euler integration. Yeah, Euler integration. But turns out we can do much better than that. We can use something that's called the Runge-Kutta method. Runge-Kutta fourth order. Now this is different from this, but this is a little bit more expensive. This only requires one calculation to get the next time step, whereas this one requires 4 calculations. And what it's essentially doing is it is approximating, it's saying, well, where would I be if I took a tiny step? And where would I be if I took a bigger step? And then it kind of averages those derivatives together with a weighted average, and then it comes up with a much more accurate to the fourth order, an estimate of the next step. And this is used very commonly. This is probably the standard workhorse of most simulations, is the Runge-Kutta fourth order. And so what you have to do is it just integrates along at some constant step size. So you have to set that step size, that delta t, and people, depending on the problem, you can use a different delta t. So if you have a very fast changing dynamic problem, say something that you are simulating a spring going back and forth, you might have to do it something like 0.01 seconds or something like that. Whereas if you're doing something like galactic simulations where things are moving very fast, but things aren't changing that much, then you could do something like maybe a delta t of days or months or something like that. So maybe say months. This would be 1 month as a time step. You could try that. And the trade-off comes in, if you do a smaller time step, you tend to get more accurate results. But if you do a smaller time step, then it takes longer. If you do a bigger time step, it runs faster, but it comes at the cost of having less accuracy, depending on your problem. So you have to kind of know a little bit about your problem in selecting your time step for your Runge-Kutta fourth order integrator. Now this is the exact same condition that you have for up here. You have to select your time step right here as well. But this is just something that you have to consider if you want to be simulating, say, like a mission, an interplanetary trajectory from Earth to Jupiter. In reality, that takes a long time, many months. But if you simulated with a 0.01 second step size, well, that would take a really long time in the computer, and so you're more likely you're probably going to do something like once every hour you'll do an update And some of the really clever schemes start doing things like saying, well, let's compute a fourth order estimate, saying let's compute to some accuracy, and then let's compute a more accurate estimate. So they might compute the fourth order and then compute the fifth order estimate. And then what they do is they say, well, what's the difference between these two? Is this difference, we'll call the difference delta, is this difference big? Is the difference small? If the difference is small, it means that the fourth order is just as accurate, is getting the answer right just as well as the fifth order, which is more accurate. So they say, well, if this is true, if this is very small, this difference is small, then that means that, hey, we can take a bigger step size with the fourth order integrator. Awesome. So if this is small, then this turns into a larger step size. But if we have a big error, a big difference between the fourth order estimate and the fifth order estimate, it says, well, this one's more accurate. So if there's a difference between this one and this one, it means that we're probably taking too big of a step size right with this one. So what we'll do is if we have a big error, we will then shrink that step size. Now these are very fancy integrators indeed. These are one in general, one that I like a lot. It's called the Runge-Kutta-Thelberg, and I might run out of space, but Thelberg 4.5, and it means it's fourth order accurate with fifth order error, which is really nice. And this does this type of clever mathematical trickery inside of itself, so that it lets you go really fast when you can, and then it slows yourself down when you need to be very careful. So it's much more sophisticated, and it's very powerful. But it's a little bit, you kind of have to know how to use it properly. It's a powerful tool, but you have to know how to use it properly, just like everything. So when we plug in our equations of motion and we integrate them forward with the Runge-Kutta fourth order or with an RKF or a Runge-Kutta-Thelberg 4.5, we can start ourselves, our trajectory, say right here, and then we say, okay, well, we can just step ourselves along, and we keep stepping, and then, hey, what do you know? We hit the ground. So you just have to put in some type of trigger saying, well, let's stop integrating as soon as we hit the ground, for example. Or you might want to say, if coming back from space on a trajectory, on an entry trajectory, you might say, well, we really only care about where we end up at this altitude. Say this is like 10,000 feet of altitude or something. So we might want to terminate there. Or we could say, well, let's stop after we've flown for, I don't know, an hour or something like that. And those are all ways that you can set up terminal conditions or termination conditions for your numerical integrator. And what you end up then is you set these triggers, and then once the trigger is satisfied, then it kills that while loop that I was showing earlier in the previous video, and it will terminate the integration, and you will have an entire trajectory sampled at whatever step size you said. So you'll get the state, the position, and the velocity at every 0.1 seconds or something like that, whatever you set your dt as. And it's really cool is you can string this together and you can plot it in things. You can find out, well, I know I was at this altitude, and here's my new profile. It's saying, well, let's say, okay, here's time on this axis, and let's say here's my altitude. You might get a trajectory that looks something like this, like, so it comes in, hits the atmosphere, starts dropping in altitude, levels out, and then comes and drops like a rock until the very bottom. So these are really cool, powerful ways that you can accurately predict trajectories. You just have to have accurate models to be able to predict it with accuracy. So what do I mean by accurate models? I'm talking about atmosphere. So you have to have a good idea of how the atmosphere works. So you could use an exponential model. We discussed that in a previous video. Or you could use a table lookup method. So you could have a table that lists altitudes and the corresponding densities, and that you can use that, or you can use a wide variety of ways. But somehow you need to be able to access information about what the density is. So you need to get the density based on some function of the altitude and your flight conditions. So usually it's just altitude, but sometimes they include flight conditions as well, like your Mach number. And then, so you need to know stuff about your atmosphere to accurately model. You also need to have an accurate vehicle model. Oop, I forgot an L there. Vehicle model. So what this means is you need to understand things like your lift to drag ratio for your vehicle. And what that really means, this is a ratio of your lift coefficient, CL, that we talked about earlier, to your drag coefficient. And we call this your L over D. So for capsule vehicles, for example, so things that look like the Apollo capsule or the Orion capsule, those have very low L over Ds. These will have L over Ds on the order of, say, maybe 0.2 to like 0.4 L over D, which means that for every unit of drag you get, you only get about 0.2 units of lift or 0.4 units of lift. So you're much more like a rock than you are like a bird. So you can't really soar with one of these vehicles. But if you have a higher L over D, you can, if you're like the space shuttle has an L over D of around like 1.1 when it's going really, really fast. We call this the hypersonic L over D for the space shuttle. The space shuttle has these huge wings and this big surface. So when it flies in, that's kind of my poor space shuttle drawing. It has this huge surface to catch wind on, and as a result it can generate a lot more lift. So it has, for every unit of drag it'll get all of that plus 10% in lift. So it's very effective at transferring its energy into lift, which can help make it fly further further along in the atmosphere and help it glide better. So this is trying to show you how you can use numerical integration schemes that we talked about up here, like Euler's method, Runge-Kutta fourth order, Archive-F 4-5, or Runge-Kutta-Fehlberg 4-5, terminal conditions. So you integrate until you hit your terminal conditions, and then once you're done, then you can grab that data and look at it and see what happens. So you can predict, kind of like a fortune teller, what's going to happen as long as you have accurate models about the atmosphere and the vehicle. See you next time.